Since ancient times, we've looked into the night skies and wondered, how far do the stars stretch out into space? And what's beyond them? In modern times, we built giant telescopes that have allowed us to cast our gaze deep into the universe. Astronomers have been able to look back to near the time of its birth. They've reconstructed the course of cosmic history in astonishing detail. From intensive computer modeling and myriad close observations, they've uncovered important clues to its ongoing evolution. Many now conclude that what we can see, the stars and galaxies that stretch out to the limits of our vision, represent only a small fraction of all there is. Does the universe go on forever? Where do we fit within it? And how would the great thinkers have wrapped their brains around the far-out ideas on today's cutting edge? To begin to get a handle on infinity, we are going to need some perspective on the numbers and scales that define our universe. One place to start is a narrow side street in Charles Dickens' London. A curiosity shop, fictional to be sure. Here you can find an unparalleled collection of stuff. Old shrunken heads, manuscripts, newspapers, books, and rare examples of impressively large numbers. From Zimbabwe comes a $100 trillion note. In late 2008, with that nation battered by hyperinflation, it was worth about $1.50 US. Go up 2 orders of magnitude to something decidedly more useful. The fastest supercomputer in history will soon hum along at 20,000 trillion calculations per second, a 20 followed by 15 zeros. You'll have to run it about a day and a half to equal the number of grains of sand on all the world's beaches. That's around a sextillion, a 10 followed by 22 zeros. That's roughly the number of stars in the visible universe. Atoms in the visible universe? That's upwards of 10 to the 78th power, a 10 with 78 zeros. Cubic centimeters? A mere 10 to the 84th, a septuagintillion. To go up from there, we turn to no less a source than the Guinness Book of World Records. The largest named number in regular decimal notation, the Buddhist time period Asamkhya, is 10 to the 140th years, or 100 quintoquadragentillions. Then there's the largest number ever used. Graham's number is a calculation of angles in a type of hypercube. If you divided the visible universe into the smallest units known, called Planck volumes, the total of those units wouldn't get you anywhere close to Graham's number. But it's still nowhere close to the ultimate ceiling. Infinity. For those who find infinity hard to grasp, even troubling, you're not alone. It's a concept that has long tormented even the best minds. Over 2,000 years ago, the Greek mathematician Pythagoras and his followers saw numerical relationships as the key to understanding the world around them. But in their investigation of geometric shapes, they discovered that some important ratios could not be expressed in simple numbers. Take the circumference of a circle to its diameter, called pi. Computer scientists recently calculated pi to 5 trillion digits, confirming what the Greeks learned. There are no repeating patterns and no ending in sight. The discovery of the so-called irrational numbers like pi was so disturbing, legend has it, that one member of the Pythagorean cult, Hippasus, was drowned at sea for divulging their existence. A century later, the philosopher Zeno brought infinity into the open with a series of paradoxes, situations that are true but strongly counterintuitive. In this modern update of one of Zeno's paradoxes, say you have arrived at an intersection, but you are only allowed to cross the street in increments of half the distance to the other side. So to cross this finite distance, you must take an infinite number of steps. In math today, it's a given that you can subdivide any length an infinite number of times, or find an infinity of points along a line. What made the idea of infinity so troubling to the Greeks is that it clashed with their goal of using numbers to explain the workings of the real world. To the philosopher Aristotle, a century after Zeno, infinity evoked the formless chaos from which the world was thought to have emerged, a primordial state with no natural laws or limits, devoid of all form and content. But if the universe is finite, what would happen if a warrior traveled to the edge and tossed a spear? Where would it go? It would not fly off on an infinite journey, Aristotle said. Rather, it would join the motion of the stars in a crystalline sphere that encircled the Earth. To preserve the idea of a limited universe, Aristotle would craft an historic distinction. On the one hand, Aristotle pointed to the irrational numbers such as pi. Each new calculation results in an additional digit, but the final number in the string can never be specified. So Aristotle called it potentially infinite. Then there's the actually infinite, like the total number of points or subdivisions along a line. It's literally uncountable. Aristotle reserved the status of actually infinite for the so-called prime mover that created the world and is beyond our capacity to understand. This became the basis for what's called the cosmological or first cause argument for the existence of God. Another century later, Archimedes incorporated actual infinity into measurements of curved lines and volumes. His method boils down to a process of summation. Place a triangle inside a circle, turn it into a square, then a pentagon, and so on. As the number of sides increases to infinity, their combined lengths equal the circumference of the circle. By slicing and dicing curves into an infinite number of straight lines, he was able to compare a variety of curves, areas, and volumes. Archimedes anticipated techniques developed 2,000 years later. And yet his ideas on infinity did not carry forward due to what the author David Foster Wallace described as a mathematical allergy that developed in response to Aristotle's potential infinity. It was Aristotle's ideas that passed into the Christian era, along with his cosmology, with Earth seated firmly at the center. That view was not universal. Islamic, Hindu, and even some Western thinkers posed alternate views that included infinite space. In European circles, the issue of infinity resurfaced during the Renaissance. In 1543, the Polish astronomer Nicholas Copernicus argued that Earth orbits the Sun, not the other way around. The old Greek spheres began to fall by the wayside when a distant supernova, then a comet, were spotted by the astronomer Tycho Brahe. These objects seemed to behave independently of the other stars. A monk named Giordano Bruno inflamed the issue by traveling Europe at the height of the Inquisition to proclaim an infinite universe. In the year 1600, he was burned at the stake for this and other heresies. Just 9 years later, in 1609, Galileo Galilei used the first astronomical telescope to show that the universe is much larger than we thought. In later writings, he even sought to discredit the distinction between potential and actual infinity. Galileo was forced to recant, and the old Aristotelian view held sway. Any attempt to assign a value to infinity, in numbers or in nature, was doomed, for that was the unique province of God. Finally, at the end of the 19th century, the mathematician Georg Cantor sought once and for all to divorce metaphysics from the abstract pursuit of math. Infinity, he wrote, had to be studied without arbitrariness and prejudice. He became known for folding finite and infinite numbers into a unified theory of number sets, considered a foundation of modern math. One of his defenders used a paradox to show how infinite sets are subject to concrete comparisons. Say you've come to stay at this grand hotel. You're in luck because here there is an infinite number of rooms. Oddly enough, you learn there are no vacancies. Fortunately, the manager says, "I can still check you in." He assigns you to room number 1 and directs you down the corridor.
Wonderful. Enjoy your stay. Thanks.
Then he goes to work, shifting the guest in room 1 to room 2, room 2 to 3, 3 to 4, and so on. So in this hotel, there's a number set that includes an infinite number of guests and rooms. Then there's that same set plus you. 2 infinite sets, yet one is a subset of the other. Being able to use infinite sets of different sizes allowed mathematicians to design equations describing continuous motion and change over time. Echoing Aristotle, a critic of the new set theory suggested that the end of the corridor is still only a potential infinity, with God representing the only actual infinity. For those who pine for humble accommodations, we'll recommend an alternative later on. Even as mathematicians embraced infinity, astronomers in the early 20th century still saw a limited universe, centered on the galaxy, a flat disk of stars. Did the limits of our vision, like the horizon at sea, conceal an infinite universe beyond? Albert Einstein, for one, believed that if that were true, then the night sky would be filled with dense starlight shining from every direction. We'd reel from the effects of infinite gravity. Arguing for a finite universe, he described a people living on the 2D surface of a sphere. To them, a beam of light moving through space would appear to go straight on an infinite journey. In fact, it follows a path determined by the overall gravity of the universe and curves back around. Like the old Greek spheres, this view of a static and limited universe began to fall by the wayside in the 1920s. Edwin Hubble and Milt Humason used the new 100-inch telescope on Mount Wilson in California to look at mysterious fuzzy patches of sky called nebulae. They found that these patches were galaxies like our own, and that some were very far away. What's more, they found that most are moving away from us. The farther out they looked, the faster the galaxies are moving. This fact, known as Hubble's law, led to an inescapable conclusion that the universe is expanding. Furthermore, if you run the clock back on this expansion, it appears that it all began in one singular moment. That moment has traditionally been described as an explosion. A Big Bang. How large the universe has gotten since then depends on how long it's been growing and how quickly. Using an array of modern telescopes, astronomers have recently narrowed the beginning to 13.7 billion years ago. Taking into account the expansion of space ever since, the radius of the visible universe, the part we can see, has expanded out to 46 billion light years. These measurements have raised anew the ancient questions. What's beyond our cosmic horizons? Is there an edge? Or does it somehow go on forever? A new set of answers has emerged from a theory designed to address questions that arose from the original model of the Big Bang. For one, how did the universe get so large? The Hubble Deep Field contains images of infant galaxies at less than 10% of the age of the universe, near the edge of our cosmic horizons. By the time one of those galaxies reached maturity, it would have moved far, far beyond our horizon. And what of all the galaxies visible at its horizons? For another, how did the universe get so smooth? In every direction you look, the density of galaxies is the same on large scales. Astronomers believe that whatever process flung the universe outward must have also blended it in its earliest moments. The theory that addresses these questions was based on the discovery that energy is constantly welling up from the vacuum of space in the form of particles of opposite charge, matter and antimatter. The idea is that in primordial times, an energy field embedded in this so-called quantum vacuum suddenly moved into a higher energy state, causing space and time to literally inflate. And our universe to burst forth. If this theory is right, then our universe is incomprehensibly large. Its author, the scientist Alan Guth, wrote that the universe as a whole would have grown to at least 10 billion trillion times the size of our visible patch. That's a 10 followed by 23 zeros. If you think that's big, a variation on the theory describes the origin of our universe as a physical process that exists far beyond it, out into the seemingly infinite void that had confounded Aristotle and other Greek thinkers. In that case, our universe would have inflated like a bubble and joined a stream of other bubble universes frothing up and expanding across an endless ocean of time and space. A related idea theorizes a cosmic landscape unfolding in vast fractal patterns. These new, more expansive visions of the cosmos are not without their paradoxes. Logically speaking, with infinite stars, infinite planets, infinite universes, you will also have infinite possibilities. The so-called infinite monkey theorem has its roots in Aristotle's attempts to illustrate the perils of thinking about infinity. Ask a monkey to type, or ask an infinite number of monkeys to type, for an infinite amount of time. You're sure to get a lot of random letters. But there is a chance, however small, that somewhere, somehow, you'll get the full text of Shakespeare's Hamlet. It's clearly absurd. Then again, consider the increasingly strange nature of our universe, as suggested by some new observations. This is where we draw your attention from the famous Hotel Infinity to a less well-appointed alternative. You're sure to get a big welcome at the old Hall of Mirrors. This ramshackle place would have thrown even the great thinkers for a loop. It represents a kind of optical illusion that may be present in our view of deep space, according to a new interpretation of data from one of the most important space satellites ever launched. WMAP was sent out to make precision measurements of radiation left over from a period about 300,000 years after the Big Bang. It revealed an intricate pattern of hot and cold spots, now thought to represent the seeds of the galaxy filaments and walls seen on large scales. The pattern was laid down by pressure waves that ricocheted through the expanding gas of the early universe. One group of scientists, looking at the sizes of these waves, suggested that some are actually mirror images of themselves. From this, they argue that the universe could be much smaller than we think. That's not the only strange new line of evidence. Tracking the movement of distant galaxies, astronomers found huge clusters moving at about 2 million miles per hour in the direction of the constellation Centaurus. With the results published in a top scientific journal, the astronomers describe an immense gravitational presence that may loom beyond our visible horizon, perhaps another universe that inflated near our own. Ideas like these may well have led to imprisonment or death in centuries past. Now they're a part of a field of study that is bursting with data and ideas. Cosmology, the study of the universe as a whole, has long been infused with metaphysics and philosophy. Today, it's steadily merging into the physical sciences. So, is the universe infinite? Scientists will continue to look for evidence of what lies beyond our horizons, and to test theories on the nature of time and space. But like the room at the end of an endless corridor, the final answer will always elude us.